Welcome back to the deep dive. Today, we are strapping in for something pretty high stakes.
Extremely high stakes.
We're diving deep into a safety training outline for critical electromechanical work. We're talking panel commissioning, high voltage testing, that kind of thing.
And this isn't just theory or, compliance paperwork.
Not at all. This is really the non-negotiable rulebook for preventing some truly catastrophic accidents.
That's absolutely right. I mean, the environment we're talking about here is just filled with immense energy. The risks are instantaneous.
So what are we talking about specifically? The big four.
The big four: electric shock, arc flash, arc blast, and of course, electrocution. So our goal today is to give you a shortcut, really, to understanding the most crucial protocols.
Things like lockout, takeout, or LOTO, and proper grounding.
The absolute bedrock of electrical safety.
Okay, so let's unpack this. We're going to start with the foundational checks. What you have to do before you even think about touching the equipment. And then we'll move straight into the single most important procedure for controlling all that hazardous energy, LOTO.
And, that initial phase is all about risk and distance. The documents we looked at really emphasize that before any work starts, you have to understand the hazards.
And keep distance.
And keep your distance. We're talking about standards like NFPA 70E. And it's not just a guideline, it's really the benchmark. It tells you the absolute minimum safe clearance you need based on the voltage.
So the boundaries are step one, but the real game changer, the thing you do that removes all doubt before you touch anything, is making sure the power is actually off.
This is where we go from theory to life-saving practice. It's the single most practical step, and the source material calls it the three-point test.
A three-point test. Why 3 points?
It's a mandatory verification loop. It's designed specifically to prevent one of the most common failures, a faulty voltage meter.
Which is a terrifying thought. So how does it actually work on site?
Okay, so step one, you take your voltage meter and you test it on a known live source, an outlet, a proving unit, whatever. You just confirm it's working.
So you know the meter isn't dead to begin with.
Exactly. Then step two, you go to the circuit you're about to work on and test it. And hopefully it shows 0 volts.
Okay, but the big fear is, what if the meter broke between testing the live source and testing my circuit?
And that is precisely why there's a step 3. You immediately go back to that known live source and test it again.
So you close the loop.
You close a loop. If it reads live again, you've just verified 3 things. Your meter worked at the start, the equipment is de-energized, and your meter didn't fail in between.
It removes any shadow of a doubt.
It's a beautifully simple closed-loop safety system.
Okay, so that verification is the final check, but it completely depends on controlling the energy source in the first place.
Right.
Which brings us to the centerpiece of all of this, LO2.
And what's fascinating here is just the sheer authority given to lockout to goat. The sources state, unequivocally, that it is the most crucial procedure.
Before any installation, any cabling, any testing.
It controls everything: electrical, hydraulic, pneumatic, any kind of hazardous energy.
And it's key to remember, LOTO isn't just flipping a switch. It is a systematic 6-step process. We should probably walk through every single one of them.
Absolutely. You skip one, you break the whole chain.
Okay, step 1, preparation and notification.
This is where you identify every single energy source, primary, secondary, stored energy, you name it, and then you notify every single person who could be affected.
Communication is the first lock. I like that.
It is.
Step 2, shut down.
And this means using the normal operating controls, the regular stop button. You want an orderly stop, not just yanking a breaker, which could damage something.
Right. So after the shutdown comes step 3, isolation. This is the physical break, isn't it?
This is the physical act. You open the disconnect switches, you rack out the breakers, you are creating a literal air gap where power cannot flow.
And then step 4, the part with the name, lockout, tagout.
Right. Once it's isolated, you apply your personal safety lock and a big, obvious warning tag. And this is where we hit the most critical rule of all.
Which is?
Each person working on that equipment must apply their own lock.
Their own personal lock. That's always seems so rigid to me. Is there ever an exception? What if someone goes home for the day and forgets to take it off?
That's a great question. And the answer really shows you how absolute this is. The rules do not allow for just cutting a lock off. There's usually a very specific, very documented emergency procedure involving, multiple layers of authorization.
So the default rule is unbreakable.
The rule is only the person who put the lock on can take it off. It ties safety directly to your personal presence and responsibility.
It's your physical stand-in on the equipment. Okay, on to step 5, stored energy check.
This is a big one. You can isolate the main power, but residual energy can still be lethal.
You're talking about things like capacitors.
Exactly. The documents specifically call out discharging capacitors.
Mm.
And for you, the learner, you need to understand.
Huh.
A capacitor can hold a massive, deadly charge long after the breaker is open. It's a silent killer.
So you have to bleed that energy off safely.
You have to. If you skip this, you can still have a fatal accident from stored energy alone.
And finally, step 6, verification.
Which brings us full circle. You use a tested, proven voltage detector.
Following our 3-point test, of course.
Following the 3-point test, you verify the equipment is definitively de-energized. Only then is it safe to work.
So once that energy is controlled, the risks shift, right? Away from shock and more towards physical injury.
Exactly. The training outline talks a lot about crush injuries during lifting and handling. You have to use certified cranes, make sure loads are balanced. A draft panel isn't just expensive, it's lethal.
But the real long-term safety factor, the thing that protects the system for years, is proper grounding and bonding.
That's where we can really deep dive. Improper grounding is called out as a massive fire and shock risk. What you're trying to do is create a path for fault current.
A path of least resistance.
A path of low impedance, to be technical.
Okay, explain that. What's the difference between resistance and impedance here? And why is low impedance the goal?
Well, think of impedance as resistance, but for AC current. If you have high impedance, it's like a clogged drain. When a fault happens, like a hot wire clutches the metal frame, that huge surge of current needs to get to ground instantly to trip the breaker.
And if it can't?
If the impedance is high, the current gets stuck. It builds up on the enclosure, making the whole panel live, turning it into a giant shock hazard and generating incredible heat.
So low impedance means the current gets out fast and the breaker trips before anyone can get hurt.
Precisely. It lets the safety system do its job. And the sources detail 2 main checks to make sure this happens.
What are they?
First, you verify that all the equipment grounding conductors, the green wires, basically, are securely connected. We're talking visual checks, torque specs on the lugs. A loose connection is a future fire.
Okay, that's one.
And second, you ensure the main panel is properly bonded to the grounding electrode system. That's the physical connection to the earth itself, the rods, the grid. Those 2 things guarantee the electricity has a safe path away from people.
Got it. And that goes hand in hand with just the mechanical integrity of the box itself.
Right. Make sure it's mounted securely, no damage, and, this is critical, all the unused openings and knockouts are sealed up. You keep dust and moisture out.
Which brings us to the finer details, like cabling. Things that can cause failures way down the line.
These are those insidious failures, yeah. The sources talk about conductor termination, using the right tools, like proper crimpers, and making sure connections are tight.
Because a loose connection means
It means high resistance, and high resistance creates heat. As current flows, it just gets hotter and hotter. That's a primary cause of electrical fires. The torque spec on a lug is just as important as the voltage rating.
And there's also the physical handling of the wire itself. I saw a mention of cable bending radius.
Yeah, if you bend a big cable too sharply, you can damage the insulation inside. And damaged insulation is no insulation at all. Plus just messy wire management. Loops of cable on the floor. It's a huge trip hazard.
So after all that, after controlling the energy, managing the installation, the final layer of protection is on you. Personal protective equipment, PPE.
Exactly. And the PPE you need isn't a random choice. It's dictated by a formal risk assessment. Specifically, the arc flash hazard analysis for that piece of equipment.
Which tells you how much energy could be released in an accident.
It measures it in calories per square centimeter. That calorie number tells you what rating your clothing needs to have.
Okay, so let's break down the layers. You start with general PPE.
Your standard stuff. Hard hat, safety glasses, EH-rated boots that's electrical hazard rated, and, cut-resistant gloves for handling sharp metal.
But then you step up to the specialized electrical PPE, and the foundation of that is flame-resistant, or FR, clothing.
And FR clothing is fascinating. It doesn't melt or ignite, it chars. And that char creates a barrier that stops the heat from getting to your skin. It's the superheated air that causes some of the worst burns.
Okay, after the FR clothing, we're talking about hands.
A critical system. You need insulated gloves rated for the maximum voltage you could encounter. But here's the part people miss. You always have to wear leather cover gloves over them.
Why is that?
The rubber is the insulator, but it's fragile. A tiny nick or puncture makes it useless. The leather protects the rubber.
And finally, your head and your face.
For any task with an arc flash risk, you need an arc-rated face shield or a full hood. An arc blast is instantaneous, a plasma explosion. That hood is the only thing between that blast and your face and lungs.
So as we wrap up, we have to talk about the last line of defense, the what if, the emergency procedures.
Right, the sources are clear. You need trained people on site. First aid, CPR, specifically for electrical injuries. You can't just wait for an ambulance. Time is everything.
And you need a way to kill the power instantly.
Absolutely.
Yeah.
Everyone needs to know where the emergency shutoffs are and how to use them without a moment's hesitation.
And what about fire?
A big one. You need to know that electrical fires are different. You can't use water on an energized circuit. You need classy fire extinguishers, which use a non-conductive agent.
So let's bring this all together. For you, the listener, what does this all mean? We've unpacked the 3-point test, the 6 steps of LOTO with that personal lock rule, and the importance of a low-impedance ground path.
This is your shortcut to really understanding site safety, moving past just compliance to truly getting the why behind the rules.
And we keep coming back to LOTO, how rigid it is by design.
It is. It's all about eliminating human error. We talked about how only the person who applied the lock can remove it. It's total individual responsibility. But it makes me think.
Go on.
Well, we've seen the whole system is built to prevent mistakes through procedure. But here's a thought to leave you with. Imagine 2 people verifying a de-energized system. They both do the 3-point test perfectly, but one of them fails to double-check that a big capacitor has been discharged. Does that strict adherence to procedure sometimes, I don't know, create a reliance on the system itself rather than a relentless focus on the danger?
Like you trust the checklist more than your own awareness.
Exactly. It's a question of human factors versus procedural perfection. And it's something for you to explore as you apply all this critical knowledge.